Okay. Hello, dear Nurat Mallim. I hope you are doing well. This is my Python script for inserting the data. I used PG8000 library and Faker library for this purpose. PG8000 for connecting database, and then creating table, executing it, and then I used Faker for creating 600,000 random data, but it's not too much random actually because I specified, for example, department. It will take one of these, and also education level, and also date time, and also years of experience, and all of this. And then okay, now I will run the code and come back when it's finished the insertion. Okay, now my data is inserted. Let me just run, for example. I have ID, department, salary, years of experience, education level, and start date, which is random. All of them like this, 600,000 data. And my queries, I will first run normal queries, such as department, when the department is equals to sales, and then also it just runs in 82 milliseconds, and also ID. When we do this, actually, without an index on the department column, the database system need to perform a full table scan to find all records where the department column matches sales, in which it just checks each row, which is inefficient, especially for large tables such as mine, 600,000. And for ID also, it will do the same. It will need to scan or sequential scan to find the record with ID equal to 1. So let me just create my hash table indexes for 3 different fields: department, salary, and start date. Okay, it already exists, so let me just drop them. First, I checked a little bit before starting, so now let me just create it again. And now when we look for department again, with a hash index on the department column, the database system can perform a hash lookup for the department value sales. If the hash collisions is minimum, this can provide fast access for records with the specified sales department, since we are just looking for sales, in which it's like a linked list. So when we just run this, it will give us 61 milliseconds, which is better than the other. So it was 82, I guess. So there is 20 millisecond advantage. And for also indexing, with hash index on the ID column, the database system can perform a hash lookup for specific ID value. Again, if hash collisions are minimum, this can provide fast access for the specified value, in which the the search space is much lesser than the department query, because in department we have several departments, like 7 or 8, and it was just checking all the sales department and then finding the corresponding value. But for ID, there's only just one specific ID for each hash, so it would perform better. So in 39 milliseconds. And also here is others. I will perform this one also. And for salary also it's the same, like ID and also start date and etc. And this last query I just selected for the other binary plus 3 purposes, so I will not test it. And let me just run this one also. It was 39 seconds salary, and this one is 40 milliseconds. And coming to the binary b plus 3, first I need to drop the hash indexes because it will mix with the others. Okay, now I will create b plus 3 index, and then when I just start from this part, actually in this part hash index would work better for this scenario, because it allows for like better efficient lookup of records based on the exact matches. It's same for ID also. No, not ID, as I remember. Just for department, like for string values, it would perform better. Like for constant time lookup. And by the way, the time complexity for this b plus 3 is O log n, and for hash index is O1 in average case, because we have one hash value for each row, for example for ID, but in normal queries it's just ON in the worst case, because it just checks all the records to find maybe it's at the end, so it's ON. And for ID, since this query involves searching for a specific ID, b plus 3 index would work better, since it supports efficient access of individual records based on the keys, and also it's ordered, so it's also advantage to quickly access the data, which is exact. So let me run this also. It was nearly same with hash index. And this one also is 3 millisecond better than hash, as I remember. Okay, and now for salary column, similar to the first query, this query involves an equality search. Therefore, hash index would work better for exact values, as I said. So like department, it will be also better in the case of ID. And for date kind of thing, b plus 3 indexes are better for because of equality searches, especially on date. Um, so it would work better on B plus tree. And also the last query, which is about B plus tree, which would beat hash tables, because the query involves a range condition greater than or equal, not equal, greater, equal, less than, or between, or I don't know, some kind of this kind of stuff. Because of its order structure, it gives us efficient access of records within a specific range, and also because of its nature, it's more faster for the ranges. So let me just show the output. It's 39. Okay, now let's check it with hash table. Okay, let me just create it again. It haven't created yet. Okay. Now let's, where was it? Okay, this one. Okay, now where was it previously? Okay, when I checked it with B plus tree, it was 39 milliseconds, but when I checked it with hash table, it's just 59. So it performs better because of range condition. So in summary, it depends on the case. Hash table or binary plus B plus tree can perform better for exact values. Hash table for range, B plus tree is better. And when we put them both together, as I know, for the database is pretty clever. So if we put range option, range condition, so if we just took B plus tree approach, but when we put exact value, then it would take hash table to access the data. So that was all about it. Thank you for listening.